So we're continuing from where we left in the last video. Make sure you've done all the problems from the last video and make sure you understood them properly. If not, just send your doubts in the comments, or you can email me directly as well. You can see that on my YouTube channel description. Okay. So A24. Suppose fx is equal to, there are three definitions of fx given. The first definition, this is for when x is not equal to 1 or 2. Okay. This here is a misprint. It's an f of 1. This is not f of 2. And f of 2 is 4. F of 1 is -3. We need to check if it's continuous. So the most probable points of discontinuity are 1 and 2. X is equal to 1 and 2. So let's see what we can do here. So let's simplify this first function. 3x, x minus 1. Bottom is a quadratic, which is going to be -3x, so -2 and -1. 2 and 1, x minus 2, x minus 1. This and this get cancelled. Okay, 3x over x minus 2. This is the function definition for all x except for 1 and 2. Now we'll check if the function is continuous at x is equal to 1. For that, we need to find the limit of this function at x is equal to 1. See if it approaches the value which is given, which is defined for f of 1. So put x is equal to 1, we get 3 upon -1, which is a -3. So yeah, limit exists and it's equal to -3. So it's continuous as well because that's equal to the function value. So first option is wrong. The function is continuous at x is equal to 1. At x is equal to 2, the function is not continuous because at x is equal to 2, it's going to go to infinity. Yep. It's going to go to infinity. The function value is going to go to infinity at x is equal to 2. So this is going to be a discontinuity. Okay. And this is the right answer. So because at x is equal to 2, the function is discontinuous. And what kind of a discontinuity is this? It's a straight up jump discontinuity, and it's going straight away to infinity. So the function value is given to be 4. This is the right value. And at x is equal to 2, or just before, it's going to be very high, and just after, it's going to be very high. It's like this. So at this point, at x is equal to 2, it's particularly defined as 4. Okay. So let's go to the next one. 25. The graph of fx is equal to 4 upon x squared minus 1 has. Okay. We're going to talk about asymptotes. 4 upon x squared minus 1. 4 upon x minus 1, x plus 1. That means at x is equal to 1 or at x is equal to -1, there are going to be vertical asymptotes. Vertical asymptotes, why do we say that? Because at these values of x, the y is going to go to infinity. It's going to approach infinity. Okay. So x is equal to 1 vertical asymptote. This is correct. The y-axis as its vertical asymptote, wrong. No. Y-axis means x is equal to 0. That's not the asymptote. The x-axis as its horizontal asymptote, and x is equal to plus minus 1 as its vertical asymptotes. Okay, this can be checked. So for horizontal asymptote, what do we check? We check what y is approaching to, the limit of this function when x tends to infinity. Okay, so what we can do is we can divide with x squared, or no need of dividing even. We can just directly place x as infinity here. If I put x as infinity, I get 4 upon infinity, which is tending to 0. Any number upon infinity tending to 0. So the limit is tending to 0. That means yes, it's going to approach the x-axis. So option C is correct, not option A. Option A is also correct, but C is the superset of it. Okay. 2 vertical asymptotes, but no horizontal asymptote, wrong. There is a horizontal asymptote at y is equal to 0. Okay. A26. The graph of y is equal to 2x squared plus 2x plus 3 upon 4x squared minus 4x has. Okay. This looks a bit complicated, but let's see. 2x squared plus 2x plus 3. The numerator is an always positive expression. So that's not going to change the value. 4x squared on 4x. I take the 4 common, x minus 1. That means x is equal to 0 and x is equal to 1. These are 2 points where it's going to go to infinity. X is equal to 0, x is equal to 1. For the horizontal asymptote, we need to check the limit. So x tends to infinity. Let's check this. This is a rational expression. Two polynomials, one in numerator, one in denominator. So following the rule, we check the degree of the polynomial, that is a 2 on both sides. Since the degree is equal, we'll get a real value. Okay. So let's divide the top and bottom with x squared. 2 plus 2 over x plus 3 over x squared. This is the numerator. This goes to 0, this goes to 0 upon placing infinity. So that's a 2 in the numerator. Upon 4 minus 4 upon x. That's a 4. 2 upon 4. Y is equal to half. This is where it approaches when x approaches infinity. This is the horizontal asymptote. So horizontal asymptote at y is equal to half, and two vertical asymptotes at x is equal to 0 and x is equal to 1. Absolutely correct. Yes. Option C is the correct one. Okay, let's go to the next page. A27. Okay. Let f of x is equal to x squared over x for x not equal to 0, and f of x is 0 for x equal to 0. Which of the following statements is or are true? First of all, f of 0 we need to check if f of 0 exists. So x is equal to 0, yeah, it does. 1 is correct. Okay. Limit x tending to 0, fx exists or not. Okay. So limit x tending to 0, f of x, let's check. X square over x, x tending to 0. Okay, so basically it's an x. The function definition is x. At x is equal to 0, it's given to be 0. At the limit x approaching 0 is again a 0. So the limit exists. F is continuous at x is equal to 0. Yes, it is, because the value of the function at x is equal to 0 is 0, and the limit of the function at x is equal to 0 is also 0 from left hand side, right hand side. So option D is correct. All three are true. All three statements are true statements. Okay. Let's go ahead. Now comes part B, the calculator active directions. So we'll see if we need a calculator. Whenever we need, I'll show you how to use it. Okay. If greatest integer of x, this is how we write the greatest integer function, denotes the greatest integer not greater than x, then limit x tending to half greatest integer of x is. So x tending to half either from the left side or from the right hand side. The integer, so this is how it's defined. Whatever x is there, we need to find the greatest integer which is not greater than x. So the highest integer less than x, less than half, is 0. Highest integer less than half is 0. Whether from the left hand side or from the right hand side, it's 0. So the limit is C, 0. You can look at the graph as well. So at x is equal to 1, the value is 1, like this. So throughout from 0 to 1, 1 not included, the greatest integer would always be 0 for all of these values, and half comes somewhere here. So from both sides it's going to be 0. Okay. B2, if this denotes the greatest integer not greater than x, then limit x tending to negative 2, greatest integer x is. Okay, now this becomes tricky. Let's see. I'm going to draw the graph here, and then we'll see how to do this. This, then this, then this. Okay, this is 0. I'm changing the color. This is 0. This is negative 1. This is negative 2. Okay. Now at negative 2, and then this here is negative 3. Okay. So from negative 1 to 0, the greatest integer is negative 1. At 0, it becomes 0. From negative 2 to negative 1, the greatest integer is negative 2, but at negative 1, it becomes negative 1. Now it's saying limit x tending to negative 2. X tending to negative 2 from the left hand side and from the right hand side would be different, as you can see from this graph. From the left hand side, we approach from here. What's the greatest integer function? This is the value. Negative 3. Just at x is equal to negative 2, it is a negative 2. And then approaching from the right at negative 2, it's this, negative 2. So the limit does not exist. And that's also the rule. For integral values, limit will not exist for the greatest integer function. For any other value, it will exist, but not for integral values. So limit does not exist. The options which we can see here don't say that, so let's check for the other options. I'm turning over the page. Okay, non-existent. That's the answer. Limit x tending to infinity, sine of x. Sine of infinity. Like I told you the last time, sine is an oscillatory function. It's an oscillatory function. At x tending to infinity, again, it will still be oscillating. So it's an oscillating discontinuity. So limit does not exist. Again, D. The function fx is equal to x square over x not equal to 0, and then x is equal to 0 at 0. Okay. Is continuous everywhere, is continuous except, okay, let's check. So what happens, x square over x, this is basically x. For all x except 0, we've been given x is not equal to 0. Okay. Now, x tending to 0 from the left hand side will give this as a 0. X tending to 0 from the right hand side will again give it as a 0. Okay. Because this is the value. And at x is equal to 0, it is defined to be 0. So it is basically continuous. There is no other point of discontinuity again. So is continuous everywhere. Okay. Next question. Questions B5 to B9 are based on the function f shown in the graph and defined below. Okay, that's quite some definition. And we need to see the graph as well. Let me turn over the page. Okay, I'm going to take this opportunity to explain a very, very important thing to you this time. That it's not always necessary that we use the function definition to solve the questions. Even the graph comes handy. Okay, so let's see how we solve questions through the graph. B5 says limit of x tending to 2 fx. Limit of fx when x tends to 2 exists, and what is its value. So if you see here in the function, this is where x is 2. X tending to 2 from the left hand side, it's approaching 0. From the right hand side, again approaching 0. Even though there's a discontinuity at x is equal to 2, it's a point discontinuity, but the limit exists and it's equal to 0. It's approaching a 0 from both sides. Okay. Had they asked that x is equal to 1, the limit would not exist because left hand limit is 0, but right hand limit is 1. This here. So at 2 it exists and it is equal to 0. A. The function f is defined on closed interval -1 to 3. We need to check whether it's defined on each point in this interval. So -1 to 3, yep, the function definition is available for all the points. So option D is correct. There's no point at which the function does not have a value. The function f has a removable discontinuity at. Perfect, good question. So how many discontinuities do we see here? First of all, I would identify the first one at x is equal to 0, second one at x is equal to 1, third one at x is equal to 2. The first discontinuity, x is equal to 0. The function is coming continuous. At x is equal to 0, the value should have been 1, but it suddenly goes down and it's continuing from there. This is not a removable discontinuity, okay? Because the function definition has changed entirely. It has not regained the same definition after the point of discontinuity. So this is not removable. At x is equal to 1, it's approaching 0 and then suddenly it goes to 1 and continues from there. Again, a not removable discontinuity because the definition has again changed and it's not a single point discontinuity. Okay. Now at x is equal to 2, it's a removable discontinuity because this one point is required. If I define f of 2 as simply 0, our problem is solved and it becomes continuous. Okay. And the limit is existing as well here. If you see in these cases at x is equal to 0 and x is equal to 1, the limit is also not existing. So it will stay discontinuous. Even after you correct one point, the function will stay discontinuous. That's why it's not a removable discontinuity. So this is a very good indication of finding a removable discontinuity for all cases or all points where the limit exists, but the function is discontinuous. Those are the points where it's a removable discontinuity. The others are non-removable. Okay, let's go ahead to the next one. Okay. On which of the following intervals is f continuous? So we need to check -1 to 0, 0 to 1, 1 to 2, and 2 to 3. Let me bring the graph here. That'll be more easy. Okay, so the graph is here now. Between -1 to 0 and both included, we're saying continuous. So 0 included, it's not continuous. A is wrong. 0 and 1 not including any. 0, 1 not including any. Yep, it is continuous. Option B is correct. 1 and 2 both included, not continuous. 2 and 3 both included, not continuous. Okay, so B is correct. The function f has a jump discontinuity at, okay, where do we see a jump discontinuity? At x is equal to 0 is 1. At x is equal to 1 is the other one. So x is equal to 1. At x is equal to 2, it's not a jump discontinuity, just a point discontinuity. So x is equal to 1 is the answer. Okay. Jump discontinuity is when the discontinuity occurs and the function starts moving from there only. Okay. B10, limit of x tending to 0, square root of 3 plus tan inverse 1 over x. Okay. Let's see this. Tan inverse 1 over x. And x tends to 0. So tan inverse infinity. When is the tan inverse value going to be, or where is the tan going to be infinity? So tan inverse. Let's draw the function of tan inverse. This is the function, the graph of tan inverse. Okay. Tan inverse of infinity, it's asking. Okay, 1 over x, 1 over 0 is infinity. At infinity, it goes to pi by 2. The value comes out to be pi by 2. So this becomes square root of 3 plus pi by 2. Okay. So let's cross verify once more. We'll check for both sides, since these are two different values. Pi by 2 for positive infinity, negative pi by 2 for negative infinity. So let's see. When x tends to 0 minus, or left hand side, left hand limit, if it goes from 0 minus, it's going to be negative infinity. Negative infinity is negative pi by 2. So square root of 3 minus pi by 2. This is the left hand limit. Right hand limit, 0 plus, that's a positive infinity. So square root of 3 plus pi by 2. Limit does not exist because these are two different values for the left hand and right hand limit. So option D does not exist. Okay, now here's a challenge, B11. Suppose limit x tends to 3 minus, or left hand limit at x is equal to 3 of fx is equal to -1, and limit x tends to 3 positive, or right hand limit at fx x is equal to 3 is -1 again, and f of -3 is not defined. Which of the following statements is or are true? Okay, so limit of x tends to -3 fx is equal to -1. Okay, we're trying to find the limit at -3. So -3 minus -3 plus, both limits exist and they're equal to -1. So yeah, left hand limit and right hand limit exist. That means the limit exists and is equal to 1 at this point, -1. This is correct. F is continuous everywhere except at x is equal to -3. At x is equal to -3, the function is not defined. So yes, it is continuous everywhere except at x is equal to -3. And it is a removable discontinuity because it's a point discontinuity. The limit exists at that point. So the function is continuing. It's just at that very point that it's not continuous. Okay. So this statement is also true. This is also true. Let's look at the options. I'll turn over the page. Okay. So all the three statements are correct. Option D. Okay. Now, challenge B12. If y is equal to 1 upon 2 plus 10 raised to power 1 over x, then limit x tending to 0 y is, okay, we need to check this. Left hand, right hand, both we'll check. 10 raised power 1 upon 0. 1 upon 0 is going to be infinity. Okay. 10 raised power infinity is going to, so let's say 10 raised power x is this. This is the graph. Okay. I start with x tending to 0 minus. Left hand limit. 1 upon 0 minus. Okay. Approximately a negative value less than 0. That would give a negative infinity. 10 raised power negative infinity is approximately 0. This here is a 0. If this is a 0 in the bottom, 1 upon 2 plus 0 or 1 upon 0, that's an infinity at 0 minus. X tending to 0 plus, that's where 1 upon 0 would be positive infinity. 10 raised power positive infinity is an infinity. 1 upon infinity is a 0. So here it's infinity, here it's a 0. The limit does not exist. D. Okay. Okay, going ahead. Question number 13 to 15 are based on the function f shown in the graph. Okay. B13. For what values of a is it true that limit of x tending to a fx exists and f of a exists, but limit of x tending to a fx is not equal to f of a? It is possible that a is equal to, okay, for what value of a we need to find that the limit exists, f of a also exists, but they're not equal. Okay, so let's see. Such points would occur only at point discontinuities. So one option is -1, the other option is 1, then 2. -1, 1 and 2. These are the only options. Now in this, the limit exists here. It's approaching the same thing. And the function is also defined at -1, but it's not equal. So -1 satisfies. At 1, the limit does not exist. At 2, the limit exists, but the function is not defined. So -1 is the only correct answer. B13 is A. Okay. Let's go for the next question. I'll turn over the page. Okay, B14. Limit x tending to a fx does not exist for a is equal to. At -1, the limit exists. 1, x equal to 1, the limit does not exist. At x is equal to 2, the limit again exists. How? For -1, approaching the same value. For 1, approaching two different values. For 2, approaching the same value. Okay. So at 1, does not exist. So option B. Okay. B15. Which of the following statements about limits at x is equal to 1 is or are true at x is equal to 1? Okay. So 1 minus exists. 1 plus exists. 1 does not exist. So 1 and 2 are only correct. Okay. The statements 1 and 2 are correct. Okay. So towards the end, we saw how we're doing things graphically as well. And if you understand the graphs well, it boosts your overall understanding of the concept as well. Because it's not just about equations or expressions. The real thing is the graphs here. Okay. So we have concluded the video, this second part. This is all of the knowledge of limits, the different questions on limits, which you would get to see on the AP Calculus papers, both included. The AB and BC papers, both included. From the next videos, like in the next parts, we would be delving into the further topics. Okay. So here till now, we've completed limits, continuity, discontinuity, asymptotes, inverse functions, those kind of things, transformations. Okay. So stay tuned, keep practicing. If you have any questions on this, or if you think the answer to any question was not up to the point, just let me know in the comments and we can discuss it again. Okay. If you want to book classes with me for AP Calculus preparation, you can go ahead and do that through my website. Okay. Thank you.